Hi, in this video today we're going to be looking at another way of writing complex numbers. We've talked about Cartesian form and the way of writing a complex number like this, a plus bi. Polar form, which we're really familiar with, r cis theta or r cos theta plus r I sine theta. That's the long version of that. The shorthand's r cis theta. I want to talk about the third way here, which is exponential form. And this is attributed to Euler, who came up with this relationship. So we can also write complex numbers in this form with a base of e to the power of I times, and theta there is the argument, and r here at the front will be the length or the modulus of the complex number. Now, just a quick overview of why you can do that, and this is what's included in your notes. And it really comes from the fact that we've got a series expansion for e to the x here. So if you look at this, this is one of the basic definitions of e to the power of any number, is this infinite series expansion right here. And this is actually a really neat way to look at it and to prove also that things like the fact that the derivative of e to the x is the same as itself. Because if you look at that function there and do the derivative, you'll see that you get 1 plus 2x over 2, which is just x. The next term here is 3x squared divided by 6. So that's just x squared over 2. The derivative of this term here will be 4x cubed divided by 4 factorial. You can see the 4 factorials will cancel, leaving you 3 factorial on the bottom. And I can keep going. So you can see that the series expansion for the derivative, just by looking at the right hand side and doing the derivative, you see we get the exact same thing as the original. So that's another neat proof that the derivative of e to the x is e to the x. Here we're looking specifically at e to the x and two other series expansions which look similar. That is sine x and cos x. They also have infinite series expansions that look like this. And this is how your calculator actually works out things when you type in sine x on your calculator. It's actually using this infinite series expansion here to get the value. So let's look at what happens when we do e to the I times theta. So we had the series for e to the x. I'm going to replace the x with I times theta now, and that gives me this step here. Now, in this expansion now, I could keep going forever and ever. I'm going to replace the I squareds with -1, and that gives me this step down here. Okay, you might think, where are we going with this? What I'm going to do now is isolate the real and imaginary parts in this expansion right here. So I'm going to take out all the bits with just the real parts. So theta squared over 2 factorial plus theta to the 4 over 4 factorial, etc., etc. And then I'm going to isolate all the imaginary parts. So we've got theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial. Now if you look back at what I had written just above here, you will see that this part here corresponds to the series expansion for cos of x, or in this case cos of theta. This part here corresponds to the series expansion for sine of theta. So what have we got? In writing it this way here, we've got cos of theta plus I sine theta, which we know is just cis theta. So that's a little proof to show, when we do this reorganizing, that we can have the exponential form of a complex number z equals r e to the I theta can be written as r cis theta, where r at the front there is the modulus and theta is the argument. So that is the key thing to highlight and to understand from this video. Let's just do a couple of examples. So if you have z equals -1, and we want to write that in exponential form, so z equals -1, I'll all the time be using my argand diagram. So I've got a number that has a length of 1 and an argument of pi. So writing that in exponential form is e to the I times pi. That one right there. there. So there's a length of 1, so we do have a 1 sitting at the front there. Z equals -1 plus I. Okay, -1 plus I. Here we are here. So I want to write that in exponential form, which just means we want the modulus and we want the argument here. So hopefully you can see, because those lengths are both 1, that the length is √2, and that argument there is going to be 3 pi over 4. So this number is just √2 cis 3 pi over 4, which when we write it in this new form, we have the modulus at the front, and we just have I times the argument. That's it, and that's how we write it in exponential form. You can see that on our calculators we can also do this using the comp to pole function. So comp to pole of -1 plus I, it gives you the answer in the form that we want it. A little bit different the way it gives the exponent, but that is I times 3 pi over 4 there. Okay, going the other way around now, if we start with something in exponential form, looking at this now, you'll start to get the feel and say, okay, this is e to the minus pi over 4 times I. That negative out there you really need to associate with the angle. So again, thinking of the eigen diagram, straight away I know that we've got a number that has a length of 1 and the angle is negative pi over 4. So here is that number there. So the length here is 1 and that angle there is pi over 4. Again, this is a great one to get your calculator out on, or of course we can work out what those lengths are to get it into rectangular form, exact rectangular form. So in this triangle that I've just drawn, I'd say something like sine of pi over 4 is equal to x over 1. So sine of pi over 4 is √2 over 2, or 1 over √2. And similarly, I would say cos pi over 4 is, sorry, I should have made that y, shouldn't I? So this is the y value, beg your pardon, and I should say that is the x value there. So cos of pi over 4 is x over 1. So again, x is √2 over 2. So we've got √2 over 2 plus √2 over 2i. That it is in Cartesian form. Next one's a little bit trickier. E to the 1 plus I times pi over 3. This one here. Before you can do it, you've got to split this up. Okay? Like that. So if you do have an exponent that is one thing plus another like this, split it up first. Now this is just a number, e. This thing here is a complex number with a length of 1 and a modulus of pi over 3. Okay, so in this case here, jumping from here to here, we've just used the calculator to get that cis pi over 3 is a half plus √3 over 2i. Or you could go through the same process that I went to, and we're timesing that by e out the front. Again, our calculator's very, very helpful here. Comp to trig gives you this step here. So you can see that that's e times cis pi over 3, hopefully. But if you use the t expand function of the previous line, it also then gives it to you in nice rectangular form. So there's some examples there of using a complex number in exponential form. There's one more really tricky one that I want to show you. Oh, by the way, these complex numbers in this form really obey the same rules that we'd expect in other exponential and logarithmic and indice laws. So for example, this index law that says when the base is the same, we add the powers. So if you have two complex numbers in this form, of course this rule will apply. Okay, so if we're multiplying two complex numbers, we know we add the arguments, and so that's true in this case here, and it's following those index laws. If we had an R1 here and an R2 here, we'd know we'd be multiplying the modulus as well. So, you know, multiplying and dividing, raising a complex number to a power, something like this would be e to the I2 theta So a complex number would have, so we put a 2 there. Okay, so we've squared the length of the complex number and we've doubled the angle. So all the same rules that we had when a complex number was written in cis theta form still apply to this form here. Okay, one more tricky one that I think is worth mentioning. That's this one here, solving e to the x plus iy equals 5, where x and y are real numbers. Alright, so we want to try and find x and y. We've got to split this up first, so our first step here is to separate the left hand side of the equation. So we've got e to the x and e to the iy. Now e to the x is just e to the x, what we're used to. Now we can think of e to the iy as a complex number with a length of 1 and a argument of y. I know that seems really strange, but we can do that now. We've made this connection. So you can see on the next step I've written it like that. E to the iy is cos y plus I sine y. I expand the brackets and now I can compare the real and imaginary parts. So this question could be e to the x plus iy equals 5 minus I, or whatever. I can compare at this step here the real and imaginary parts of the complex number. So this part, e to the x cos y, that's the real part, and that's 5. The e to the x sine y part, that's the number in front of the I, is equal to 0. So now we've got a few equations that we can solve. For the first one, e to the x cos y equals 5. Actually, let's start with the right hand side. This is equal to 0. Obviously, e to the x is never equal to 0, so we don't have to consider any values of x that makes that 0. What we're looking for is the y values. So in this case, sine of y equals 0. That's going to happen for all values of y, 0, pi, 2 pi, 3 pi, 4 pi, etc. So all integer values of pi, and actually negative integer values as well, but we'll just consider the positive ones now, as going to be all the possible solutions there for y. If we now go back to our first equation over here and think of, okay, let's say we've got 0 as one possible solution. Let's solve that. So if we put 0 in there, cos of 0 is 1. So we get e to the x is 5, so x is ln 5. So there's a solution. X being ln 5 and y being 0. And in fact, if you put any of those different values of y into there, for example, pi, you're going to get a slightly different solution. So let's look at that. So if we had y is equal to pi, we would get this. When y is equal to pi, cos of pi is negative 1. The cos of 180 degrees is negative 1. So then we get negative e to the x equals 5. Or e to the x equals negative 5. Go ln at both sides and we get something that does not make sense. Okay, so you'll find that all of these solutions for y, all the even numbered multiples of pi will work. So if I chuck in 2 pi for y, I'm going to get cos of 2 pi, which is 1. And in each case, the answer is x equals ln 5. If I try and chuck in 3 pi or 5 pi, any of the odd numbers, we get this thing down here. No solution. So here's my final answer. X is ln 5 and y is any even numbered multiple of pi. That's it.